Okay, physics. Physics. Someone left me a message and asked me if I was sure that the answers at the back of the book for the questions that I gave for homework were right. Honestly, I don't know. Um, so I didn't have my books in front of me when they asked me. So just really quickly, I'm gonna give you the answers that I have, and hopefully they're the same as the back of the book. So for number 13, I got that the range was 58.9. I got that the maximum height was 21 meters and that the time interval was 4.14 seconds. For number 14, I got that the angle was 33.2 degrees. If you said 33, that's fine. I got that the max height was 2.39 meters and that the time interval was 1.40 seconds. Um, yeah, I think that's it. I think that was the ones that you had the questions on. I think so. Maybe not. Maybe the questions were on the ones for the circular motion. If you are finding that your answers are different than the back of the book, tell me specifically which ones, and I can look that up for you. I do have my handy dandy binder at home so that I know that. We are headed to actually the end of a chapter very shortly here. There's not a lot left, to be honest with you. So I think I said this on Friday, but I'll say it again today. I have that we're going to do a test on chapter 11 on Friday. This one is sort of a mix of theory and math. So I think we'll do it via Zoom because that way I can see you at least do the theory portion of it. It cuts out after 40 minutes, but supposedly for educators it's not supposed to, so I applied to be labeled an educator. I don't know. Anyway, we'll see what happens. So I have a test on Friday. Now we're actually going to finish up chapter 11 today, and I'll review it tomorrow, answer any questions that you have, just kind of jog your memory on what's in that chapter. I will give you a study day on Wednesday. On Thursday, I'm actually going to start into chapter 12. Chapter 12 is like 11. It's not very long. Actually, I think usually I only get to the end of chapter 13 in physics. And actually 11, 12, and 13 are all fairly short. So we probably will actually get there. Normally, I have days missing for drama practices, days missing for CAT testing, and the big one, sorry guys, but I usually have days where we don't get anything done because of the grad trip. Unfortunately, those aren't happening. So that means I actually have a few extra days. So even though I'm going slower through the material than I normally would, we still may get to the end of everything, just because we're gaining some days in there that I don't normally have. So chapter 11, sorry, my book's on the wrong page, I was reading ahead. Chapter 11, we were talking last time, we were talking about angular momentum and centripetal force. So one of the things I want to talk about, I'm just trying to find the page, sorry guys. Here we go. So there are actually two different terms that we use in the real world. There's centripetal force, and sometimes you will hear people say the word centrifugal force, centripetal and centrifugal, or centrifugal, depending on where you're from. One, centripetal force is a real force. It is a center-seeking force in rotational movement. It is a force that pulls you to the center. It's a real thing. Centrifugal force is, remember way back we talked about the term fictitious forces. A fictitious force is a force that your body interprets as a force, but it isn't really a force. That's what centrifugal force is. It is an imaginary force that you feel when you're in an accelerating frame of reference. Okay? So again, if you're moving in a circle, your car is going around a curve, and you feel like something is pushing you to the outside of that curve, nothing is really pushing you to the edge of the car to smush your sibling beside you. Nothing's actually pushing on you. What's actually happening is your body's trying to go straight as the car is turning. That's a fictitious force. There isn't actually a force there. So centripetal force is a real center-seeking force that is provided by some other type of force, be it force of gravity, force of friction, force of tension. So it is a center-seeking force that is provided, and the definition for it is in the PowerPoint. If I ask you to define that on a test, hint, then that wasn't too subtle, was it? Then you need to give me the PowerPoint definition, because that's the definition straight from your textbook. Don't give the sort of kind of definition, which is what I just gave you. I gave you the sort of kind of definition. Give it word for word. All right, so centripetal force, real force. Centrifugal force, not a real force. All right, it's a fictitious force. It's something that your body feels that it interprets as something pushing on you or a force on you. I'm skipping that section. All right, so the other thing I want to talk about is this idea, is this idea of banked curves. So I'm going to make you think for a minute. So if we ever get to fly in airplanes again, think about flying in an airplane. When your airplane is flying and it has to change direction, it has to turn. You can tell that you're turning when you're in the plane, because what happens is the plane turns to one side. If it wants to turn left, then it dips its left wing so it can turn. Why does it do that? Why can't it just turn left? Why does it have to go up on its side a little bit in order to turn? And again, the sharper the turn, the more it has to dip, right? Why does it do that? So some of you are going, I never thought about that before. Of course you didn't. Before I had to teach physics, I didn't think about it either. All right, so let's talk about why that is, okay? When an airplane is flying straight, the design of the wings and the flow of the air over them creates a force that we call lift, okay? It creates a lift force. And that's what keeps the airplane in the air, which always freaks me out a little bit. The only thing that is actually holding you in the air is the fact that the wings are shaped the way they are. And when the air flows over it, it actually creates this little air pocket underneath the wing, which holds it up. Kind of freaks me out a little bit that that's the only thing it's the only thing holding it up, guys. All right, so the lift has to be equal in magnitude and opposite in direction to the weight of the airplane in order for the airplane to remain on a level path. So if you have your airplane, here's its wings, and you have the airplane, the lift has to be directly opposite to the weight or the force of gravity. If the force of gravity is more than the lift, you sink, all right? So that's not good. So it has to be the same. Um, so when the airplane banks, when it goes to turn, what happens is, so now the airplane is like this, okay? Lift always works perpendicular to the wings of the plane. So now your lift is going actually this way. Force of gravity is still pulling straight down. So what happens? Well, in order to create a turn in anything, in order to create circular or like a turn, you have to have a force supplying that. And we talked about, like, when we swing a yo-yo, it's the force of tension that keeps it in that rotational motion. A car going around a curve, it's the friction of the tires on the road that supplies the force needed for centripetal force. So when you're in the air, what is supplying the force needed in order to turn, to get the centripetal force to turn? Well, when it banks, what happens is that lift force is now going diagonally, okay? And so now we can break that apart into its components. We can have the Y component of the lift, which is working against gravity. So again, there has to be enough lift to counteract gravity, or you sink. The X component of the lift is the part that is center seeking. It is the part that is supplying the force needed for centripetal force. So that's why an airplane has to bank. It has to turn. It has to go at an angle. Cars have to do the same thing. When a car is driving down a road, the only thing keeping it on the road is friction, the friction between the tires and the road. That's the only thing keeping it there. When you go around a curve, then part of that friction has to go towards centripetal force, keeping it on that curved path. But there's a problem with friction. What friction does is it wears down your tires. And so if every time you went around a curve, and the higher the speed, the more friction. So if you're on a highway and you are driving very fast and you have to take a turn, if it's flat, the only thing providing that centripetal force to make it go in the curve is friction. That's going to wear out your tires. And for me, for my truck, a set of tires can run anywhere between $1,000 and $2,000. I don't want to have to replace those all the time. Not really good for the environment either. So, and if it's icy, if there's not a lot of traction, how am I going to keep the car going in a curve if there's not a lot of friction there? So what engineers do is they bank the road. They kind of put it at an angle a little bit. You're going to start noticing these things when you drive, because physics kind of bugs you that way. It sticks in your head and you start noticing stuff. But you're going to notice when you go on an off ramp or onto or even some on ramps, they're banked. That's not because the ground was curved there. It's because they created that. And so what it does then is, when you bank the curve, so here's your car, when you bank the curve, your normal force is here, force of gravity is here, and what happens is that force of gravity, or normal force, can help to keep that on. So banked curves on a road function in a way that is similar to the banking of an airplane. The normal force of the road on the car provides centripetal force when the road is banked, since a normal force is always perpendicular to the road's surface. So normally it's just friction, but if the normal force is slanted here, just like in the airplane, some of that normal force will go to counteract gravity, but some of that normal force will now help contribute to centripetal force, and it won't all be coming from friction. Now, they show you on page 564 how they derive the formula for this. And if you're in grade 12, here's a heads up. Part of that is they end up with sine over cos, one of those trig identities, and they turn it into tan. Again, if you want to look at it, if you're interested in how they come up with this formula, it's on page 564, halfway down. Even if you wanted me to explain it, I could, but I don't want to get into the where does the formula come from too much, because I tend to freak people out and confuse people. Suffice it to say, in order to figure out how much do they need to bank that curve, okay? How much do they need to tilt it? They have a formula worked out. And that formula looks like this. Tan theta, that's a theta, sorry, is equal to v squared over r times g. So v, obviously velocity, r, radius, g, acceleration due to gravity. So let me show you how this works. And this really is all there is to it. Okay, it's not really all that scary. Canadian Indy race car driver Paul Tracy set the speed record for time trials at the Michigan International Speedway in the year 2000. I don't know if anybody's broken it since then. I'm not a car racing fan. Tracy averaged, holy cow, 378.11 kilometers per hour. Okay, I've had my truck up to like 140 by accident. I didn't do it on purpose. My truck goes fast and I didn't notice. I've had my truck up to 140, but 378.11, that seems very, very fast. The ends of the 3-kilometer oval track are banked at 18 degrees. So they've banked the curves 18 degrees. So, whoop. And the radius of the curvature is 382 meters. So when you talk car racing, if you've ever watched any of it at all, what you'll notice is there's not a lot of grooves, there's almost none, on race car tires. There's a reason for that. They actually want to minimize friction because friction slows them down. So they actually want to minimize friction between the tires and the road. They're always playing the game of how little friction can I get away with and still stay on the road, right? They're always trying to figure that out. How smooth can I make the tire and not wipe out? So they really want to bank those curves because there's not a lot of friction contributing to the centripetal force to get them to turn. Most of their, or not most, they would like a lot of the help to come from the normal force. I wouldn't say most, because as you're going to see, but. So they asked two questions. At what speed can the cars go around the curve without needing to rely on any friction to get that centripetal force, to get that turning action? So if they wanted to say, listen, I don't want friction to play a part at all, how fast would I be able to go around that curve and have my speed, my velocity all come from the normal force and leave friction out of it? So I'm going to take this formula. I know the angle, it's 18 degrees, is equal to v squared over r. My radius is 382, needs to be in meters, times gravity, which is 9.81. So v, I'm going to take tan of 18, multiply it by 382, multiply it by 9.81, and then take the square root. Don't forget to take the square root. So when I do that, tan 18 times 382 times 9.81, and then I take the square root of that, I get 34.89 9, and I can have 3 significant figures. So 34.9 meters per second is the velocity. That doesn't really help me much when I'm looking at it compared to 378.11 kilometers per hour. Because my next question says, did Tracy rely on friction for some of his centripetal force? So in other words, if he was going 378.11 kilometers an hour around that curve, was all of his centripetal force coming from the normal force, or did he need some friction there from his tires? Well, the max you can go around without using friction is 34.9 meters per second. So we need to figure out what that is in kilometers per hour. So for those of you who hate converting, I'm sorry. Meters per second. So here's what I do. There are 1,000 meters in 1 kilometer. I put meters on the bottom so that they will cancel. And there are 3,600 seconds in an hour. 3,600 seconds in 1 hour. Now again, I put seconds on top because it's on the bottom here, so they'll cancel. And the units I have left are kilometers per hour. So across the top, 34.9, and I just didn't erase this, times 3,600, and then divide by 1,000. It is 125.6 approximately. So you can go around that curve at 125.6 kilometers per hour. I've actually gone that fast. You can go around the curve at that speed and never need friction to hold you there. But he was going 378 kilometers, almost 3 times as fast, which means he actually needed quite a bit of friction to keep him on the road. All right, so that's it. We are at the end of chapter 11. I'm going to give you a few questions to try. Please let me know if you have any questions. You guys have been doing a really good job at that. Hopefully I've been doing an okay job at responding. I try. If at any point I miss your question, please just tell me. I'm not trying to ignore you. You would not believe the amount of emails, messages, Google Classroom messages, Google Hangout messages. You would not believe the amount of information coming at me. And you know me in organization, it doesn't work. So if I miss you and you still don't get it, just ask again. I just missed it, all right? Again, I'm not trying to ignore anyone. I'm not an organized human. All right, so that is today. There'll be a few questions there for you for homework. We will be done chapter 11, review tomorrow, study day on Wednesday, start into chapter 12 on Thursday, test on Friday. It'll be a Zoom meeting. All right, talk to you soon.